In this video, we look at precipitation reactions in more detail and examine how to predict if a precipitation reaction will take place at all, and if so, how to determine the products of precipitation reactions. Precipitation reactions are an example of a double displacement or metathesis reaction, which involves a double exchange of reaction parts. As a quick recap, let's look at this general reaction scheme here. AB plus CD goes to AD plus CB. What's happening here is A is displacing C to form the compound AD, while at the same time B is displacing D to form the compound CB. In effect, what we have is a swapping of parts, with substance A coming together with substance D and substance C coming together with substance B. The example shown in the picture at the top right is a precipitation reaction that takes place when a solution of lead-2 nitrate is mixed with or reacts with a solution of potassium iodide. And in fact, what happens with precipitation reactions is a swapping of cation and anion pairs between ionic compounds in solution with, in this case, the lead-2 ion displacing or swapping places with the potassium ion to form the lead-2 iodide compound, which is the yellow precipitate that is formed. At the same time, the nitrate ion is displacing or swapping places with the iodide ion to form an aqueous solution of potassium nitrate. The net effect of this precipitation reaction is the coming together of lead-2 plus ions with iodide ions in a 1:2 ratio to form the bright yellow solid precipitate lead-2 iodide, which is an insoluble salt. The equation here is referred to as the net ionic equation, and it stems from the full molecular equation shown here, which shows that when lead-2 plus ions are in the presence of certain anions, such as the nitrate ion, they are quite soluble and will readily form aqueous solutions, as indicated by the AQ subscript. Similarly, when iodide ions are in the presence of certain ions, such as potassium ions, they are also quite soluble and readily form an aqueous solution. However, when lead-2 plus ions and iodine ions come together, a chemical transformation occurs, with the solid PbI2 or lead-2 iodide being formed. The other product formed is potassium nitrate, which by our solubility rules we can determine is soluble in water, hence the AQ subscript. So a couple of questions we could ask ourselves. If we were to mix two aqueous solutions together, how can we predict if a precipitation reaction will actually occur? And how can we predict what the products will be? We can answer these questions by going through a systematic step-by-step process. Step 1. We write the formulas of the reactant solutions in the form of a molecular equation. So, for example, if the two aqueous solutions were silver nitrate, AgNO3, and barium chloride, BaCl2, we would write their full chemical formulas out like this. The next step, step 2, is to assume that the reactants actually react, and we write down the products based on a double displacement metathesis reaction. That is, we swap the anion and cation pairs around. And so the positively charged silver cation is now going to hook up with the negatively charged chloride anion, and at the same time the positively charged barium cation is going to hook up with the negatively charged nitrate anion. And so all we've done is just swap the cation and anion pairs. The next thing we have to do is make sure the chemical formulas of these two potential products are actually correct. So if we look at silver chloride to start with, silver is a 1 plus ion and chloride is a 1 minus ion. So when they come together to form an ionic compound, the 1 plus charge and the 1 minus charge cancel each other out and they will come together in a 1:1 ratio. So AgCl is the correct chemical formula for silver chloride. But what about barium nitrate? Is this the correct chemical formula for barium nitrate? Barium is a group 2 metal. It forms a 2 plus ion. The nitrate ion is a 1 minus ion. These two ions will not come together in a 1:1 ratio. If we do our crisscross method, we take the 2 from the 2 plus charge of barium and bring it down as the subscript for nitrate. And we can take the invisible 1 from the 1 minus charge of nitrate and bring it down as a subscript for barium. And so what we end up with is the formula for barium nitrate being Ba1 NO3 in brackets 2, or simply BaNO3 2. And you will recall we insert the brackets around the polyatomic nitrate ion when we have more than one polyatomic ion in a chemical formula. So we need to make sure we make that correction and ensure that we have the correct chemical formula for barium nitrate. And we should also point out at this stage that if any chemical formulas are written incorrectly, you will find it very difficult, if not impossible, to balance the overall chemical equation. The next step, step 3, is to balance the chemical equation. And remember, all we can do at this stage is to put the appropriate stoichiometric coefficients in front of each substance. Also, another point about balancing chemical equations involving polyatomic ions is to keep the polyatomic ions intact if they appear unchanged on both sides of the equation. In other words, we don't try to balance the individual atoms separately. So for example, we can see that we have one nitrate ion on the left-hand side and two nitrate ions on the right-hand side. The idea here would be to balance the nitrate ions as a whole. The other atoms not balanced at the moment are the chlorine atoms, with two chlorides on the left-hand side and only one on the right-hand side. To balance this equation, we can place a big 2 in front of the silver nitrate on the left-hand side and a big 2 in front of the silver chloride on the right-hand side. So this equation is now balanced. In step 4, we're going to use our solubility rules to determine if any of the products will in fact form an insoluble salt. And we will insert appropriate subscripts to each product, either an S subscript if an insoluble solid precipitate forms, or an AQ subscript if the product is soluble in water and forms an aqueous solution. To do this, we go to our solubility table, and we see that most chloride salts are soluble in water, but there are exceptions, and one of them is silver chloride. So silver chloride will require an S subscript to indicate that a solid precipitate will form, as shown in the photograph here. In terms of barium nitrate, we see that all nitrate salts are soluble and there are no exceptions. So barium nitrate will require the AQ subscript indicating it exists as an aqueous solution. A last step that may be required is to write out the net ionic equation from this full molecular equation. To do that, we first have to write out the full ionic equation from this full molecular equation, and then identify any spectator ions and cancel them out from both sides of the equation. So let's have a go at doing that. Starting with our full molecular equation, we get to the full ionic equation by writing out all strong electrolytes in the full molecular equation as separated individual ions dissolved in solution. So the silver nitrate solution separates into two silver ions and two nitrate ions corresponding to the stoichiometric coefficient of 2. The strong electrolyte barium chloride separates into a barium 2+ ion and two Cl- ions. The silver chloride solid is not a strong electrolyte, it is not soluble in water, so we keep it written as 2AgL solid. And finally, the strong electrolyte barium nitrate separates into the barium 2+ ion and two nitrate ions. Now we can see that the nitrate ions on the left-hand side undergo no physical or chemical change going from the left-hand side of the equation to the right-hand side. These ions are therefore spectator ions. They don't take any part in the reaction, and we can effectively cancel them out. The other spectator ions that undergo no physical or chemical change are the barium ions. So that just leaves us with the two silver ions and two chloride ions on the left-hand side, and the 2AgL solid on the right-hand side, resulting in our net ionic equation at the bottom, which you will notice has a stoichiometric coefficient of 2 in front of every substance, meaning we can effectively cancel them out to get our chemical equation down to the lowest whole number ratio of all substances involved. And now we have our net ionic equation of one silver plus ion and one chloride minus ion being transformed to produce solid silver chloride. To summarize the steps in predicting the products of precipitation reactions, we write the chemical formulas of the reactant solutions in the form of a full molecular equation. We assume that the reactants actually react and write down the products based on a metathesis double displacement reaction. In other words, we swap the anion and cation pairs. We then balance the equation, making sure we write down the correct chemical formulas first, and then we use our solubility rules to determine if any insoluble solid precipitate will form. And then finally, if you need to write out the net chemical change that actually happens, then write out the full ionic equation, cancel out any spectator ions to give the net ionic equation.